and I will speak just for 1 minute to introduce the presentation, which will be given by Dr. Fabio Tossani, who is already the co-host of this session. Just to thank PowerSys for the invitation, thank PowerSys for the cooperation that we are having together. This cooperation resulted in this line of code, which is part now of the EMTP code by PowerSys. The 30 seconds more I will take of your attention are just to underline some aspects of this code, which will be illustrated more precisely by Dr. Fabio Tossani. This code starts years ago with a cooperation with the Polytechnic Institute, Federal Institute of Lausanne, EPFL, and in particular with Professor Farhad Rashidi, and at that time also Professor Michel Janos, Professor Carlo Mazzetti of University of Rome, La Sapienza, and myself in Bologna. We did this, and the aim was to describe the electromagnetic coupling between the lightning electromagnetic pulse radiated by a lightning return stroke and an overhead line. We started with a simple case, which was a single conductor line, first on a perfectly conducting ground. Then we added complications. The ground became non-perfectly conducting. The line became multi-conductor. We added shield wires. We added surge arresters, nonlinear components along the line. We thought that it was more useful to interface our code with another code which was capable of taking into account all these complexities, which is EMTP. And so that was the basic idea. Of course, we wanted to test our code against a large number of experimental results, and we did it. And the nice thing is that this code has been used by the most recent IEEE standards and SIGRE standards on the subject. That is it. And I now leave the floor very willingly, with pleasure, to Fabio Tossani. Fabio, the floor is yours.
Thank you.
Thank you so much again.
Can you hear me well? Can you see the screen?
Yes, you are audible and your screen is also visible. Thank you.
Okay. First of all, I want to thank you very much for the invitation. And as you see, the title of this presentation is LEMP and ground conductivity impact on the direct lightning performance of a medium voltage line. Is a presentation of some results that we obtained within the framework of a joint research project between the Japanese CRIEPI and the University of Bologna. You can see here the authors of this presentation and the members of the project, which are Professor Borghetti, Dr. Kishimoto, Professor Napolitano, Professor Nucci, and myself. So, in medium voltage distribution lines, lightning and flashover outages are associated to indirect strokes and are less frequent when surge arresters are installed at close interval. In this case, indeed, the lightning performance is mainly determined by the line response due to direct strikes, usually assessed disregarding the effect of the lightning electromagnetic pulse. So this keyword LEMP stands for lightning electromagnetic pulse. So indeed, when lines are very well protected, including surge arresters, overhead lines like typical Japanese lines, you indeed have limited danger due to indirect voltages and LEMP coupling to the lines, and you generally are focused on the overvoltages due to direct lightning strikes to the conductors or the shield wire. Instead, the focus of this presentation is to examine the influence of the LEMP effect, so the electromagnetic pulse coupling with the line, also in case the event you consider is a direct strike to the conductor. So this, yes, the effect in particular of the light of the lamp on voltages across the insulators caused by indeed the direct lightning for, in particular, lines over a lossy ground with different values of the ground conductivity. So since in this presentation I will give only an initial inspection of the overall amount of results that we got from this project, I give you here the 3 papers that you can read in case you are interested in digging more into the topic. So let's consider now our distribution line. This is a 3-phase distribution line with an overhead shield wire. The ways in which we can, the ways in which lightning can generate overvoltages in this line are due to direct strikes, in particular in case of shielding failure, in case the direct lightning hits one of the phase conductors, or back flashover in case a direct strike occurs on the shield wire. The third way is an indirect strike, which induces on the line an overvoltage due to the LEMP coupling with the line itself. So in representing these 2 different phenomena, generally when we deal with the direct strikes, we focus on representing the current injection into one of the conductors of or the shield wire. The focus of this project is to assess if the LEMP has an impact also in case of direct strikes. So can we neglect the LEMP effect when a direct strike occur on the line? Generally, in the literature, you find this type of calculation made by injecting a current source in the EMTP line, and you neglect typically the LEMP effect. So let's now see what are the results in case we take into consideration also the LEMP effects. So concerning the models and tools that we adopted in the analysis, generally the response of a power distribution overhead line to a direct lightning strike is obtained by means of different methods. We focused on the following 3 in this project: EMTP, which simulates the line response assuming the direct strike can be modeled by means of an equivalent current source, therefore neglecting the LEMP effect. And then LEO EMTP, in which we consider the LEMP effect. We take into account the LEMP effect in the calculation by using the LEO toolbox implemented in the EMTP environment. And finally, the finite difference time domain, which since it intrinsically considers both the effects of the current injection and the LEMP coupling with the light conductors, can be considered our benchmark. Okay, so it solves the full wave problem, the full wave Maxwell equation. So it will be our benchmark for testing our calculations. This is the model in the model of the line we consider in. It's been implemented in a 3-dimensional FDTD calculation. This is a typical Japanese 6.6 kilovolt distribution line. You see 3-phase and the shield wire. The pole is reinforced concrete that is represented by a rebar inside the poles. Just a few notes on this 3-dimensional FDTD model. This is the model developed by Criepi. You can find more details in this publication here at the bottom of the page. So it's used to simulates all the line, the lightning, and all the environment around the line and the lightning channel. All the conductors are represented in the distribution system, which includes phase conductors, cross arms, reinforced bars, and the inside concrete pole are also taken into account. These are the dimension of the space, the cells, and the details concerning the retrostroke model and the conductivity values that we have taken into account. So we start from 10 millisiemens per meter up to 1 millisiemens per meter. The relative permittivity is kept constant in all our calculations. Concerning the LEOV code, this is a representation how the coupling equation are implemented inside the LEOV code. And particularly, we focus here on the components that are due to the external lightning electromagnetic pulse, the LEMP. And these are instead the components for which the ground resistivity, the ground conductivity, plays a major role in the calculation of the line parameters. As you see here, this is a transit ground resistance of the line, and the calculation of the electromagnetic field. You can neglect the dependency of the vertical component of the electric field on the different values of the ground conductivity, but the ground conductivity influence very much the horizontal component of the electric field. So the LEOV code, as Professor Nucci has introduced, has been interfaced with the MTP, and therefore practically the LEOV code calculates the LEMP and the coupling, and then the MTP calculates all the boundary conditions and makes available a large library of power components. So you can see here the web page for the LEOV MTP toolbox, and a few words more concerning the LEOV. LEOV has been extensively validated with experimental campaigns throughout the years, and the LEOV code is also used in the IEEE standard for improving the lightning performance of electric power overhead distribution lines. I would like to show, for instance, here the calculation of the lightning performance obtained by LEOV code for different ground conductivity values and or different types of grounding of the shield wire. So now let's go back to our model. This is how we implement in LEOV MTP the line. So we use a 3-phase and shield wire medium voltage distribution line, and we set the surge impedance of the concrete pole to 300 ohms. And then we implemented a grounding resistance model for the concrete pole and the grounding itself. Okay, so basically in steady state, it's more or less 20 ohm and 200 ohms for the two different values of the ground conductivity. These values have been estimated from the 3D FDTD calculation results. This is how you implement in EMTP the line. You see a couple of LEOV lines for representing also a possible stroke on the midspan of the line. Then you have pole models, which includes the pole and also the grounding, and the injection of the idler function. The LEOV line intrinsically allows you to consider also the presence, the effects of the LEMP coupling with the line. Span length of the line is 40 meters. Inside the models of the poles, you can also include surge arresters, as we have did here in this figure. You can include a model for representing the flashovers. For instance, the integral method here is used. We inferred this value from experimental results obtained by CRIEPI. And finally, we implemented a grounding model of the line. This is a quite simple grounding model, which takes into account also the soil ionization. So we assume the direct lightning, and the 4 reinforcing bars inside the concrete pole behave as down conductors and grounding electrode. to estimate the grounding resistance, we, from the radius and burial depth of the concrete pole, we used this Liu and Darvenisa's formula. Okay, this is the effect of the soil ionization taken into account for different values of the ground conductivity taken into account into the study. You see the grounding resistance with the increasing value of the current injected tends to decrease due to the soil ionization. And this is the effect represented for all the different ground conductivities considered. We injected the two different currents in order to represent a first stroke and a subsequent stroke. The model for the current waveforms at the channel base is by means of one or the summation of two idler functions, which are the function represented here. Okay, now let's talk about the LEMP effect in the most simple case, in which we don't have a surge arrestor and which we don't consider, in the case in which we don't consider flashovers. Okay, so it's a little bit ideal situation because you see very large overvoltages are expected to be generated in the line, and therefore assuming no flashovers in such a distribution line, it's a little bit didactical. Okay, but now let's focus only on the polarity of the effect of the LEMP. You see here in the left side the case without considering LEMP effects. Without considering LEMP effect, you have an injection in of a current into the shield wire, which is directly connected to the cross arm with a metallic bar. So negative, we consider negative lightning. Therefore, the polarity of the induced of the generated overvoltage is negative. And for mutual coupling, also the phase wire is assumes a negative polarity. The difference between these two voltages is the voltage across the phase insulator. In the second case, the voltage at the cross arm is more or less unchanged because the dominant effect is the injection of the current in the shield wire. But on the contrary, in this case, we have an increase of the polarity of the phase wire due to the induction effect taken into account by considering the LEMP coupling by means of the Liob toolbox. And therefore, the result is an overall increase of the voltage across the insulators. So in this particular case, you see that the effect is quite big. You expect, due to the presence of the LEMP, a voltage that it's more or less 370 kilovolt instead of 180, 190 kilovolt without considering LEMP. So in this particular case, the LEMP effect is apparently important. These results are calculated with the EMTP, case A, and Liob EMTP, case B. So now the next step is to verify if the results are expected, the result calculated with the Liob are matching the ones of our benchmark, the FDTD results in 3 dimensions. In order to do so, we consider again a first stroke and a subsequent stroke hitting one of our poles, and we compare the results predicted by FDTD in black with respect to the ones obtained by Liob EMTP and EMTP without considering LEMP. And you see that indeed the FDTD and Liob EMTP results are in good agreement, and we should expect an increase of the voltage across insulators due to the coupling of the electromagnetic field with the line conductors. This stands for both the cases of a first stroke and a subsequent stroke, hitting pole number 1 here in the line. Of course, hitting the shield wire. This is another case in which we introduce surge arresters. You start seeing that if we introduce surge arresters, this effect, this enhancement due to the LEMP coupling is minor with respect to the case in which no surge arresters are installed. another case, a different position, more or less the same consideration can be drawn. And therefore, we move now to the results obtained for different values of the ground conductivity. For different values of the ground conductivity, you see here the first figure is without considering LEMP. So just considering the ground potential rise variation due to the grounding behavior implemented in EMTP. The central and right figure instead are the LEOV, EMTP, and FDTD results. You see again that a good match is obtained between LEOV and FDTD results for all the considered ground conductivity. So by summarizing, the LEOV, EMTP, FDTD results show a larger overvoltage with respect to the overvoltage calculated only by considering the injection of the current in EMTP. So we can conclude that the LEMP effect enhances the voltage across insulators. Another case with considering surge arresters. For the moment, we don't consider flashovers yet. In this case, you see that, as we expected, the results coming from EMTP are the influence of the LEMP is reduced by the presence of the surge arrester. So again, a good match between LEOV, EMTP, and FDTD results. But this time, let's say the difference between the peak amplitude obtained without considering LEMP and with considering LEMP are minor. So again, summarizing, the influence of the LEMP is reduced by the presence of surge arresters, and FDTD and LEOV show a good agreement also in this case. This is the trend of the ratio of voltage across insulator with LEMP with respect to the case without LEMP for different values of the ground conductivity in abscissa. You see that in case no surge arrester is considered, left figure, we have an enhancement of the ratio of the overvoltage peak as the ground conductivity tends to increase. The case in which surge arresters are installed every 200 meters sees an increasement of the ratio, but this increasement is very limited with respect to the case without surge arrest. So we can conclude that the higher the ground conductivity, the larger the ratio of the maximum insulator voltage considering LEMP with respect to the case in which we neglect LEMP. So as a confirm, the influence of LEMP is curbed by the presence of surge arresters. What we can do now is try to calculate the lightning performance of the line by using a Monte Carlo method. The Monte Carlo method generates a large number of lightning events. These lightning events are represented by their position, their location with respect to the line, the peak amplitude, the equivalent front time, maximum steepness, and time to half value of the lightning current at the channel base. We assume that the events follow a log normal probability distribution for negative first strokes. And from the total set of lightning events, we distinguish between direct and indirect events by adopting an incidence model for the line. And then we calculate the overvoltages and the maximum overvoltage for both the case of direct and indirect strikes. In this case, we will focus on ND, which is the number of direct event exceeding the withstand voltage of the line. But if we take into account also the breakdown of the insulators with the integral method in order to represent the flashover, this will be the number of events that will generate a flashover in the line. A is the striking area that we consider, and G is the annual ground flash density. We normalize everything to one flash per kilometer square per year. And tot is the total number of events that we consider in the Monte Carlo procedure. And E, which is here disregarded, would be the number of indirect events that generate overvoltages larger than the withstand voltage of the line. So this is the representation of the calculation area of the Monte Carlo simulation. We consider only direct strikes that hit the line, and we calculate the flashover annual number of flashover FP like this. We consider 20,000 events that corresponds to 2,450 direct strikes to the shield wire. These are the results in terms of flashover rate number per 100 kilometer of line every year. In case we consider, in case we don't consider the LEMP, it's the white column, the white bar, sorry. In case we consider the LEMP, the gray bar. So without surge arrestor, we see that we have an increase, significant increase of the expected number of flashovers. In case surge arrestor are installed, the increase is somewhat minor. This Monte Carlo simulation is very powerful because let us distinguish single phase discharges, single phase flashovers, and multi-phase flashovers. So flashovers involving more than one conductor. Again, in case without surge arrestor, we have a very meaningful increase of the expected number of flashovers in case LEMP is considered. In the second case, with surge arrestor, we have an increase, but it's minor with respect to the case without surge arrestors. Now we focus on the effect of the ground conductivity, and we focus on the flashover probability. So instead of considering all the area, all the and events per year, we focus on this ratio, which is the flashover probability. Okay, in this chart, in this figure, we see that the flashover probability is influenced by the ground conductivity, as we expect on the basis of the time domain results that we have shown in the previous slides. And we see that in case surge arrestor are not present, the case in black here, the effect is the reduction, the increase of the flashover probability is very large. Okay, you see, for instance, here we have 70% for a ground conductivity of 10 millisiemens per meter. In case you don't consider the LEMP, the probability is 20%. Okay, so it's very, the effect of the LEMP appears to be very important. In case we consider surge arrestor, the effect is limited. You see here, the trend is that the flashover probability tends to decrease, of course, if the ground conductivity increases, but the effect of the LEMP is major in case surge arrestor are not present. In order to generalize, the larger the distance between subsequent surge arrestors, the more important will be the effect of the LEMP. Okay, let's keep to the conclusion. Sorry for the wrong effect in the presentation. So, some concluding remarks that we can draw from these results. Powerful models and engineering tools are fundamental for lightning protection and insulation coordination of transmission and distribution lines, as they allow for the assessment of the lightning performance of transmission or distribution system having realistic or complex configurations. They allow for the proper choice and location of the most adequate protection means in terms of shield wire, surge arrestor distance, as we have seen, so on. The LEO VMTP toolbox can be successfully applied to modern smart grids as it considers the presence of all types of power components, includes the EMTP library, accurate pole lines, grounding configurations, the possibility to calculate multi-phase flashovers considering the insulation breakdown model. Conclusion from the results that we have obtained by this calculations is that the LEMP effect have been shown to be capable of worsening the lightning performance of medium voltage distribution lines, especially when they are scarcely protected by surge arresters. Okay, that's it. I thank you for your attention.